Welcome everyone. In this video, today we are going to see the next type of a passive device used in microwave circuits. It is called as microwave resonators. In our 12th science or maybe physics, you might have come across a term called as resonant frequency. So usually we can construct a resonant frequency using RLC circuits or oscillators or filters. They may use different resonant frequency. So creation of such resonators at microwave frequency, how it will be done, that we will see in this particular session. So first of all, what is microwave resonator, or what is it is also called as microwave cavity resonators. A cavity resonator is a metallic enclosure that confines the electromagnetic energy. That means a closed body to which a frequency or signal of a particular frequency will be applied, and electromagnetic energy generated by that signal will be enclosed within that particular body. So that body is nothing but our cavity, and electromagnetic energy which is stored inside that body will be at the maximum possible value, and this happens only at particular frequency. Okay, at other frequencies the energy may not be maximum. So the stored electric and magnetic energies inside the cavity determine its equivalent inductance and capacitance. Now we know that resonance can be obtained by using a simple RLC circuit. Sorry, simple RLC circuit. Now, whatever energy which is stored by that cavity will be equivalent to inductor and capacitor, L and C. So L and C correspond to storing of energy. Now, inside the cavity, not entire energy generated will be stored. Some of that energy will be dissipated also, or it will be drained out by the cavity also. So energy dissipated by the finite conductivity of cavity walls is determined by its equivalent resistance. So why does energy is leaked or dissipated? Because the cavity walls, which are metallic, they will have certain conductivity, and they will conduct that energy to the external atmosphere, and that is denoted by the resistance of that particular wall. Okay, so energy stored is concerned with the L and C, whereas energy dissipated is concerned with the resistance of the walls. Okay, in practice there are several types of resonators. Some of them are rectangular cavity resonator, circular cavity resonator, and reentrant cavity resonator. These resonators are commonly used in the microwave application. So we will restrict our discussion to only these three types of microwave resonators. At microwave frequency, simple R, L and C are not useful because these are lumped elements, and lumped elements do not work well at the microwave frequency. This we have known since the beginning of this particular course. So RLC resonators are not used in the microwave frequency. You have to go for some different solutions for generating resonators or creating resonators at microwave frequency. You can use transmission lines, we can use cavity, that is waveguides, and different other devices which can be used for constructing resonators. So first let's look at the rectangular cavity resonator or cavity resonator in general. First of all, theoretically, a resonator has an infinite number of resonant modes. Okay, now we are talking about cavity. Usually, it will be a waveguide or transmission line for microwave frequency. So, obviously, since it is a waveguide, it will have a mode associated with it. Then, the modes which are providing resonant frequencies, those will be called as resonant modes. So, such resonant modes will be infinite for a given cavity, and each mode corresponds to a specific resonant frequency, and vice versa. A resonant frequency corresponds to resonant mode, and resonant mode corresponds to a resonant frequency. When a frequency of, of an impressed signal, that is a signal which is inserted into the cavity, if that signal's frequency is equal to a resonant frequency, then maximum amplitude of the standing wave occurs. That means let's assume uh, this is my cavity. I have inserted one signal here. Now, when this signal has a resonant frequency, the maximum amplitude of standing wave occurs. Maximum amplitude of standing wave occurs. Otherwise, for non-resonant mode, the amplitude may be smaller also. Okay, and the peak energies which are generated because of these standing waves are stored in the electric and magnetic fields uh, of the electric and magnetic fields store of the standing wave inside the cavity walls. They will be equal. Okay, so at resonant frequency, E and H will be equal. Okay, the mode having the lowest resonant frequency is known as the dominant mode because it will be easiest to generate, and that's why it will be dominant in the entire operation. So let's look at the rectangular cavity resonator. On your screen you can see the diagram of a rectangular cavity or rectangular waveguide also. Now if you compare this diagram with the geometry of a rectangular waveguide which we have discussed previously, here you will see three dimensions have been shown, that is A, B. Now here third dimension D is also essential. In the waveguide, we were not discussing D because the propagating wave through the waveguide was propagating for infinite distance. Okay, but in this case, our wave has to limit itself or has to be confined within this particular geometry. It should not go beyond this geometry. So all the waves will remain inside this particular geometry. That's why D is also important in the resonator. So apart from that, the working of the resonator will probably or will mostly in the case this case will be similar, but now the third dimension is important to enclose the wave inside the waveguide. Okay, so how this can be constructed? Simple. We know that this one and this one, these two entry points of a wave are open in case of waveguide. Now let's close them. So how to construct them? Resonator can be constructed from closing the section of a waveguide by shorting the ends, both ends, front end and back end, to form a closed box, or it is called as a cavity now because it is closed one. Now it will store a electromagnetic energy and power can be dissipated in the metallic walls as we have already discussed. Also, if cavity includes the dielectric medium, power will be dissipated inside the dielectric medium of the cavity also. This is the dielectric medium. Okay, so simply close the box, you will get a resonator. Open the box, it can serve as a waveguide, simple waveguide. The electromagnetic field inside the cavity, as in the case of waveguide, it should satisfy Maxwell's equation subject to the boundary conditions that electric field tangential to and magnetic field normal to metallic walls must be vanished. So what's the meaning of this statement? Inside this particular cavity, whatever electric and magnetic field are generated, that they should satisfy Maxwell's equation. That is also applicable in case of waveguides. Now, boundary conditions in the resonator will be expanded from side boundaries or side walls to now front and back walls. So this is my first wall to which I am going to apply boundary condition, and this is the second wall to which I am going to apply boundary condition because now this is closed one. Okay, now after applying the boundary condition, electric field tangential to electric field tangential to, that means E in this case, and magnetic field normal to metal walls. Magnetic field normal to metal walls. Sorry, this is M, not E. Electric field tangential to the metal walls and magnetic field normal to metal walls. Magnetic field normal to metal walls and electric field tangential to metal walls. They should vanish. That means Ex and Ey should be 0 at this particular two walls. I'm again repeating. Let's delete this one. Now Ex and Ey, these will be components tangential to this particular wall. So they should be 0. And if you are talking about TM mode, that is transverse magnetic mode, then normal component should be 0. This is normal because this is the wall. The arrow directly into the wall will be normal to that particular wall, and that should be 0. Okay, so let's see this equationally. The wave equations in the rectangular resonator should satisfy the boundary conditions of 0 tangentially at 4 of the walls, all the 4 walls. Previous or side walls I will already discussed in the waveguide. Now 2 more walls have been added, that is front and back. So Ex and Ey should be 0 on the walls. Z is equal to 0 and D. Now we have seen how to find out the values of electric field component by considering Hz. So it is necessary to choose harmonic functions in Z. Why harmonic functions? Because we are concerned with the resonator. So in the case of Z, that is direction of wave propagation. This is the direction of inserting a signal. So wave will propagate in this direction. So in Z direction, harmonic function should be satisfying the condition. These functions can be found out by Hz is equal to H0z cos of m pi x by a, m pi y by b, and p pi z by d. Again observe the third term, which is a sine term, sine of p pi z by d. This is added compared to waveguide, that is for TE mode. Now mode here is mentioned in 3 subscripts M, N and P. In waveguide it was denoted by only M and N because front and back wall were open. Now H0Z is a first harmonic of that particular wave in the Z direction. M, N and P will have different values. M values will start from 0, N values also start from 0, but P values, that is in the direction of dimension D, they will start from 1 because they have to be existent. Okay, E is equal to existent for direction of D, and E will be 0 for X and Y. That's why M and N starts with the 0. Okay, so these numbers represent number of half wave periodicity in the particular direction, like half wave periodicity in the X direction, half wave periodicity in the Y direction, and half wave periodicity in the Z direction. So what is the meaning of half wave periodicity? So again go back to the previous case or previous geometry. Now half wave periodicity means for m is equal to 1, m corresponds to x direction, so this direction, half wave periodicity. As m is equal to 1, the wave will be, electric field component will be like this. For n is equal to 1, electric field will be like this. Okay, now that will be confined within the wall, so it will be like this. Okay, these are the m is equal to 1 and n is equal to 1. This is m and this is n. Okay, and for p is equal to 1, the half wave periodicity will be like this. This is p is equal to 1. Okay, now what if m and p values are 2? For m is equal to 2, half wave periodicities are 2, so wave will be like this one. This is half wave and this is another half wave. For n is equal to 2, again for n is equal to 2, this will be uh, like this. Okay, full circle or full sine wave. And for p is equal to 2, it will be like this. Okay, these are the half wave periodicities. As you increase the number of uh, m, n and p, number of half waves will increase. Half wave means half circle. This is one half wave, these are two half waves. Then when you have three half waves, it will be like this one: first, second and third. So these are the half wave periodicities, and these are denoted by m, n and p. This is the equation of Hz, which is required for TMNP, that is TE mode. Similarly, in case of TM mode, we will require to calculate Ez. Again, x and y components will be sine and z component will be in terms of cos. And now if you observe here, m, which is in direction of x, starts from 1, and in direction of y starts from 1, but now p, which is direction of z, start from 0, because if this is your wall, this is your normal to the wall, that will be in the direction of d, that is d, and it has to be 0 for TM mode. Magnetic field component has to be 0 for TM mode, and that's why p should be 0 in that case. Okay, so again half wave periodicities for m, n and p same as the TE mode, but this is the equation for TM mode. A resonance wave number for the rectangular waveguide or rectangular cavity can be defined as k, similar to waveguide, and it can be found out by same formula: k square is equal to m pi square upon a square plus n pi by b bracket square or p pi by d bracket square. Here the third dimension is also added. So for finding out which will be the resonant frequency, you can use this wave number formula for calculating resonant frequency. For lossless dielectric, that means if within the cavity there is no dielectric or a dielectric which is lossless, k square will be equal to omega square mu epsilon. Mu is a permeability, epsilon is a permittivity. In such scenario, resonant frequency can be found by Fr is equal to, general formula is Fr is equal to k upon 2 square root of mu into epsilon. Substitute the formula for k from this equation in this particular equation, we will find this answer for resonant frequency. So for T and TM mode, in case of rectangular cavity, you can find resonant frequencies from this formula. Now, as we have discussed previously, a mode with the lowest resonant frequency is a dominant mode. So we can calculate which will be a dominant mode by substituting different values of m, n and p. We know that uh, conventionally a sorry conventionally dimension a is always greater than dimension b, and dimension d will be much greater than both a and b. So if b is less than a, b is less than a, and a is less than d, then it is a normal rectangular cavity, that is normal rectangular waveguide with both ends closed. The dominant mode in such rectangular waveguide is T10, and that's why the dominant mode in the rectangular cavity will be T101. Okay, here it is mentioned T101 corresponding to T10 dominant waveguide mode. and the waveguide of a guide wavelength of lambda g by 2, and transmission line, if it is a transmission line, cavity is made up of if transmission line, then short circuited lambda by 2 transmission line can be used for generating this kind of rectangular cavity. The dominant TM resonant mode for rectangular waveguide is TM11. So dominant TM resonant mode for rectangular cavity is TM110 mode. In general, how to excite or how to insert a signal for this particular cavity: simply insert a straight wire probe at the position of maximum electric intensity in order to obtain a desired mode, as you can see in this diagram. Here we have inserted a signal probe. This is the input, so you will get, this is one half wave, this is another half wave. Now this is also a half wave, because this is a quarter wave and this is a quarter wave, that makes it a half wave. So this is for m is equal to 1 and n is equal to 1. Okay, this is also another way of inserting a probe. Here also m is equal to 1, n is equal to 1. So these are the different ways with which resonance can be obtained, and maximum amplitude of standing wave occurs for that particular resonant frequency. Okay, so this is the working of rectangular cavity resonator. Most of the part in this further in this particular module are theoretical one. You don't have to derive the equation for cavity resonator equations, like how this particular equation has come. You don't have to derive that. So this is rectangular cavity resonator. Then similar to that, there will be a circular cavity resonator, or it is also called as cylindrical cavity resonator, because we are using cylindrical coordinates for analyzing them. A cylindrical cavity resonator or circular cavity resonator can be constructed. We know how cylindrical or circular waveguide looks like. It looks like this one. Okay, so which ends are open? These ends are open in waveguide. Now close them. Okay, so constructed from section of circular waveguide shorted at both ends, top and bottom ends, similar to rectangular waveguides. Because the dominant circular waveguide mode is TE11, the dominant cylindrical cavity mode is TE111, similar to rectangular. Circular cavities are often used for microwave frequency meters. So these resonators can be used in different microwave applications, such as VCOs, that is voltage control oscillators, CROs, cathode ray oscilloscopes, frequency meters. Then in case of musical instruments also this can be used. So that is the best example of a resonator where musical instrument produces maximum sound at only particular frequency. That analogy can be used here for understanding the concept of resonator also. So cavity constructed with movable top wall allows mechanical tuning of the resonant frequency. So you can mechanically adjust the tuning frequency of the resonator by keeping top wall movable, and the cavity is loosely coupled to a waveguide through a small aperture. So small aperture will be created at the top wall, and you can move that top wall to adjust your resonant frequency. In operation, power will be absorbed by the cavity as it is tuned to the operating frequency of the system. So if you want to measure how much power is absorbed, you can connect a power meter also elsewhere in the system. So let's look at the geometry now. The wave function in the circular resonator again should satisfy Maxwell's equation, similar to rectangular cavity resonator. Again, boundary conditions have to be applied. Now boundary conditions are added for top and bottom wall also, as you can see in the diagram. For cylindrical coordinates, we are considering rho, which is denoted by this particular radius A. A is the radius of this cylinder or circular waveguide. Now it is a direction of rho. Phi is angular distance, and Z is a height of the particular cavity. Okay, so in that case, how half wave will be observed? Let's see. This is there is slight correction here. We are using a notation n, p and q for rho, phi and z. We will use notation n, p, q. So this is q is equal to 2 and q is equal to 1. Okay, so keep that or in your mind or make that correction while taking out notes. Q is equal to 1. There will be a single half wave in the z direction. For q is equal to 2, there will be two half waves in the z direction. E rho and E phi will be 0. Okay, similar to rectangular waveguide, we will also analyze this one. In the rectangular waveguide, ex and ey were had ex and ey were 0, and in the circular waveguide, e rho and e phi will be 0. Okay, for TE mode. So let's consider TE mode again, and the remaining two components, remaining two end walls components will be obtained, that is electric field component at this wall and this wall, that is in z direction, will be obtained by using equation for hz, which is given by h0z, Bessel function of a first kind, that is n of x dash npr upon a. Now what is x dash npr? During the circular waveguide analysis, we have seen p dash np. Now here we have used x dash np. Different books use different notations. P dash np and x dash np both are same. What is p dash np or x dash np? It is the root of a derivative of a first kind of Bessel function. So what is the derivative of first kind of Bessel function? Derivative of first kind of Bessel function is Jn dash, and root of this Bessel function is p dash np or x dash np. Understood? Jn is a Bessel function, Jn dash is a derivative of Bessel function, and p dash np is a root of that particular derivative. Okay, Jn is the first kind of Bessel function. Then cos n phi sin q pi z by d. Using this equation, you can find out hz, and then you can find out ez from that one using Maxwell's equation. Okay, so similarly to the rectangular cavity resonator, n, p and q is the number of half wave periodicity in different directions, phi, rho and z. Okay, if you observe, p and q are 1, n starts from 0. Jn is the Bessel function, h0z is the amplitude of the magnetic field, and for Tm mode you have to calculate Ez. Again, Bessel function, its root can be found out. Now here x dash n, x and p is given, that is p and p, which is a root of Jn, not z dash n. Okay, that is a slight difference. Again, the convention is same for denoting the equation. So this is how you can find out different components of electric and magnetic field. Now the aim is to find the resonant frequency for this circular waveguide or circular cavity. So the separation equations means different frequencies at which resonance will occur. That's why they are called as resonance wave numbers. For T and Tm modes can be obtained by these two formulas. First one is for T mode, second one is for Tm mode. Simple formulas. M pi by a square is replaced by now x dash np by a bracket square, and m pi by a square is replaced by xnp by a bracket square for Tm mode. Once you get this wave number, it is easy to find out resonant frequency applying the same formula that we applied for rectangular cavity resonator. Use the formula for k square in that formula, and you will get frequency of resonance for TE and frequency of resonance for Tm mode by using these two formulas. It is interesting to note that TM110 mode is dominant where 2A is greater than D. So if your rectangular cavity has a larger A, so large that it is also greater than D, that is 2A is greater than D, then TM110 mode is a dominant mode. But if D is greater than 2A or equal to 2A, that means if you consider a, sorry, that was a rectangular waveguide. I am talking about a circular waveguide, so it should have been circular. So if D is greater than 2A, that means height of a circular waveguide is too large compared to the radial distance or angular distance, then dominant mode is a TE111 mode. Okay, this is D is greater than 2A, and this one will be 2A is greater than D. Okay, for different dimensions, different dominant modes, TM110 for 2A greater than D and TE111 for D greater than 2A. Okay, so that is all about rectangular and circular cavity resonator. Uh, in this we have seen what is a resonator, where it is used. Resonator is primarily used for storing the electric and electromagnetic energy. It can be used in VCOs, filters, oscillators, CROs, frequency meters, different applications. But cavity resonators are used only at microwave frequency. At lower frequency we can use RLC circuit, simple. Now walls of the energy consigned or confined within the cavity is represented by L and C, and energy dissipated will be represented by resistance. Then rectangular type of cavity resonator and circular type of cavity resonator we have seen. Now in the next video we will see another type, that is re-entrant cavities, but that is for next session. That's all for today. Thank you.